In the current and following videos, we will see that among all DFAs recognizing a given language, there exists one of them that has less states than any of the others. We call it the minimum DFA. We start analyzing this example of DFA. Imagine that we are in the middle of a run and that we are either in a state A or in a state D, but we don't know which one of them. If then the run ends, in any of the possibilities the automaton is accepting. In other case, if we read a 0, we will stay either in a state A or D. We don't know which one. If we read a 1, then we will be in a state B or E. We don't know which one. If the run ends, in any of the possibilities automaton rejects. But if we now read a 0, we will go to state C or F. We don't know which one. If the run ends, regardless of the case, it is rejected. Else, if we read a 1, we will move to C or F. We don't know which one. If we now read a 0, we move to states B or E. We don't know which one, but the word would be rejected regardless of the case. All this gives the intuition that the states A and D are equivalent in the following sense. The accepted words starting the run from A are the same as the words accepted starting the run from D. The states B and E are also equivalent in this sense, and so are the states C and F. This notion of equivalence will be used to reduce the size of the DFA. For instance, intuitively it seems that this transition from E to D with a 1 could be diverted to A, since the language recognized from A and from D is the same. And this transition could also be diverted to A, for the same reason. In this case, D could not be reached and we could remove it. In the following, we will further explore these ideas in order to reduce the size of a DFA until finding the minimum possible DFA recognizing the same language. Let A be a DFA. We define the following relation between states in A, denoted in this way, or ignoring the A like this. Two states Q and Q prime are equivalent or indistinguishable if the languages recognized from them are the same. This is analogous to say that, for any word W, from Q we reach an accepting state after reading W, if and only if, from Q prime we reach an accepting state after reading W. It is easy to see that this is an equivalence relation, that is, reflexive, symmetric, and transitive. Recall that, whenever we define an equivalent relation over a set, we have the quotient set, that is, the partition in equivalence classes. In the previous example, this is the quotient set. This is the usual notation to represent the equivalence classes of a given element. In our example, the class of A coincides with the class of D, and it is this one. We will prove that, when two states are indistinguishable or equivalent, after reading the same symbol from them, we reach a pair of states that are also equivalent. Note that this property can also be written in this way. If the equivalence classes of two states are the same, after reading a symbol from both of them, we reach a pair of states such that their respective equivalence classes are the same. Let's prove this property. We start with the hypothesis, which is that Q and Q prime are equivalent, and we consider some symbol A in sigma. By the definition of equivalence, we have that any word W reaches an accepting state from Q if and only if W reaches an accepting state from Q prime. In particular, any word starting with A reaches an accepting state from Q if and only if it reaches an accepting state from Q prime. This implies that any word reaches an accepting state from state QA if and only if it reaches an accepting state from state Q prime A. This is precisely that the states QA and Q prime A are equivalent, which is what we wanted to prove. Now, using all these definitions and properties, we define the quotient automaton under the relation of indistinguishability. The states of A quotient are the equivalence classes. The initial state of A quotient is the class of the initial state of A. The accepting states of A quotient are the classes of the accepting states of A. The transition function is defined in this way. From a class of a state Q, after reading the symbol A, we reach the class of QA. We have defined the automaton. It remains to be seen that this new automaton recognizes the same language than the original one. This is equivalent to say that for any word W, from Q0 we reach an accepting state reading W with the automaton A, if and only if from the class of Q0 we reach an accepting state reading W with the quotient automaton. This sequence of equalities, obtained by applying the definition of the transition function of the quotient automaton, justifies that reading W from the class of Q0 we reach the class of Q0W. We still need to see that Q0W is in F, if and only if the class of Q0W is an accepting state of the quotient automaton. But this is straightforward because, by the definition of quotient automaton, the class of a state is accepting if and only if the state is accepting. This concludes the proof. Going back to our example, this is the resulting automaton. Note that the states are the three classes of equivalence that we had. Before, from A with a 0 we reached D. Now we stay in the same class. Before, from A with a 1 we reached B. Now we reach this class with a 1. Note that this is equivalent to say that before, from D with a 1 we reached A, and now from here we reach this state with a 1. The justification for the remaining of the automaton is analogous. Also note that the class that contains the two accepting states is accepting, and that the initial class is the one where one of its elements was the original starting state. It remains to be seen the algorithm to compute the equivalence classes and justify that the constructed automaton is the minimum among all the possible automata for the same language.